The James Webb Space Telescope continues to collect images from all throughout the cosmos, including planets in our own planetary system, with every captivating image it captures. We thought about our most memorable quick look at images of Stephan's Quintet, the Carina Cloud, and, most notably, the captivating deep field photograph a year ago. This particular image satisfies the James Webb Space Telescope's assumption by clearly showing several galaxies loosening up into the vast expanse of the universe. It has not stopped at a maze. In recent years, it has uncovered objects that contradict conventional wisdom in cosmology. Cosmologists now refer to these astounding discoveries as universe breakers, perplexing the scientific community with their ability to challenge accepted theories. The reasons for these discoveries are yet unknown, which confuses our theories and conjectures. What has the James Webb Telescope revealed recently? What astounding new information has it made available to us that we didn't know existed before? Come explore how the James Webb Telescope has challenged the accepted theory of the Big Bang by introducing data that points to the existence of an additional universe. According to a theory called the Hot Big Bang, our cosmos evolved from a denser, more smoldering condition. The discovery of the cosmic microwave background, CMB, a remnant from the early hot and thick state, in the 1960s provided overwhelming evidence for this theory, which has been a major scientific achievement throughout the past century. The Big Bang Theory has continued to be the most widely accepted explanation for the beginnings of our universe. Nonetheless, cosmologists and astrophysicists are now addressing the Big Bang itself, as well as the ongoing expansion due to fresh and important data. The fact that other hypotheses have not gained traction in spite of these obstacles emphasizes how persistent the hypothesis of the universe's genesis is. The prevailing opinion is that the origin of the cosmos is described in terms of a denser, smaller universe in the distant past. The existence of photons that resemble radiation suggests that the universe was hotter at first and has since cooled. The regular laws of physics break down at around /10⁻⁻43 seconds, and the density, temperature, and energy levels approach a position where a singularity could emerge when extrapolated backward in time. Small distances, short lengths, and high energy scales test our understanding during this brief period, reversing the enormous clock to the hypothetical 0 point. Massive quantities of particles and antiparticles would have been produced if the universe had begun as hot and thick, then expanded and cooled, with any extra particles being destroyed by radiation. The four fundamental forces and particles with non-zero masses were the result of the electroweak and Higgs symmetries breaking down as temperatures dropped. Protons and neutrons combined to form composite particles known as quarks and gluons as the universe cooled further. Deuterium, helium-3, helium-4, and lithium-7 are examples of light nuclei that were created when protons and neutrons combined. Large-scale structures formed about 380,000 years after the Big Bang as a result of radiation pressure-induced expansion in dense regions, followed by gravitational collapse. A critical point where photons decoupled and their frequencies extended as the universe expanded was reached when the universe cooled enough to produce stable neutral particles. The early astronomical explosion theory was the most widely accepted explanation for the universe's formation when the cosmic microwave background was discovered many years ago. The steady-state hypothesis's ardent proponents, such as Fred Hoyle, continued to defend increasingly implausible assertions despite overwhelming evidence, whereas the majority of cosmologists and astrophysicists accepted the Big Bang idea. It was conclusive evidence, not reflected heat from dust or blurred starlight. The cosmic glow was remarkably uniform in all directions, like an ideal black body, but it was unrelated to any known things in the cosmos. Nevertheless, by endorsing tentatively incorrect ideas, Hoyle and his supporters persisted in impeding scientific progress. Between the 1960s and the 2000s, space science and cosmology both saw remarkable expansion, with cosmology experiencing particularly notable breakthroughs. We gave a broad overview of the vast cosmos and explained its structure. We examined the development, expansion, and dynamical relationship between galaxies and their populations of stars. But even with these developments, we ran into contradictions that were hard to reconcile with the Big Bang idea. Disparities shown by observations cast doubt on the dominant force of the origin idea. Most significantly, there are no exotic particles. like magnetic monopoles or particles from grand unification, that the hypothesis predicted. These forces are still enigmatic at the universe's inception, but they seem to be necessary for the cosmos as we perceive it today. The theory of the universe's origin finds it difficult to explain the universe's need for an exact expansion rate in order to balance the total energy density. Given the universe's size and rate of expansion, this theory fails to provide either a firm balance or sufficient time for energy exchange across various regions of space. The scientific community and cosmology face serious difficulties as a result of these abnormalities. Two strategies come into play when theories are unable to explain observable anomalies: either improve on current theories or look into other possibilities. The most promising theoretical framework for expanding the Big Bang perspective was the inflation hypothesis. Inflation smooths out the universe and gives it uniform qualities, suggesting a period of fast development. It forecasts the emergence of quantum fluctuations, which show up as changes in temperature and density, thus solves the horizon problem. The validity of inflation is supported by the fact that its forecasts match observable patterns and fluctuations. Even though there are other theories, inflation is still the strongest scientific theory. Nevertheless, despite his dedication to singularities and general relativity, Roger Penrose's work, including his partnership with Stephen Hawking, was unable to keep pace with inflation's progress in describing the early cosmos. In recent years, deliberate efforts have been made to discredit inflation theory in favor of conformal cyclic cosmology, which is inherently problematic from a scientific perspective. The main difference between both is seen in their predictions. Conformal cyclic cosmology claims that the cosmic microwave background and the universe's large-scale structure contain relics of a cosmos that existed before the Big Bang. The boundary between inflation and a hot Big Bang, on the other hand, should be causally independent of any pre-Big Bang domain, according to inflation theory. Every facet of our universe demonstrates remarkable properties, indicating that we should trust the universe itself to reveal the truth instead of merely depending on theory and ignoring early shocks. Anomalies in the photos sent by the James Webb Space Telescope starting in 2022 were instantly identified by cosmologists. These discoveries might call for a re-examination of important facets of the universe's beginnings and development. The existence of completely formed galaxies considerably earlier than predicted by the conventional model of cosmology was one important finding made by the Webb telescope. This discrepancy calls into question the accepted order of events that follows the Big Bang, which states that stars and black holes emerge first, then galaxies develop. These insights upend our comprehension, much like when grandparents are portrayed as children in a narrative. Furthermore, new evidence has exposed flaws in the basic theories of the universe, such as the persistent disparity in the measurement of the Hubble constant that endures despite advancements in data collection techniques and precision. Moreover, more fresh information from the Webb telescope adds to the problems with the present cosmological paradigm. These problems draw attention to shortcomings in the model itself, raising questions among physicists and cosmologists. Over the past 50 years, the model has been modified to accommodate new data, although some contend that these modifications have been overly practical. As a result, there is increasing recognition that a change in viewpoint would be necessary, which could alter our understanding of the basic characteristics of the universe. Edwin Hubble's groundbreaking discovery of the expanding cosmos in the 1920s led to the development of the Standard Model of Cosmology, which is celebrated as a triumph of human knowledge. The theory of the universe's origins was supported by later discoveries, including as the cosmic microwave background radiation in 1964, which described the early universe as a hot, dense soup of subatomic particles that cooled steadily over time. However, theoretical extrapolation beyond observable data has been necessary to reach the current degree of accuracy in cosmic comprehension. To address discrepancies in earlier Big Bang models, inflation was proposed in 1981, underscoring the special character of cosmological theory. This theory states that for a short time after the Big Bang, the early cosmos experienced extraordinary, fast expansion. This concept solves certain problems, but it also creates new ones, particularly in light of the widespread view that there is only one universe and maybe countless more that are out of our line of sight. Indirect evidence supports some observable abnormalities, such as hypersingularities within black holes. But given the Webb Space Telescope's amazing findings on galaxy evolution and the persistent problem with the Hubble constant, there are worries that we may be at a turning point where a significant improvement to our current cosmological model is required. This might call for a reconsideration of the basic components of the cosmos, including the essence of life itself. In contrast to many other scientific disciplines, cosmology addresses important issues regarding the cosmos, its beginnings, and the function of observers in it. The study of quantum physics and consciousness explores similar topics, examining the meeting point of theory and reality and challenging key presumptions that underpin human comprehension. Scholars like physicist Lee Smolin and scholar Roberto Mangabira Unger have challenged conventional wisdom by arguing that physical principles may change and evolve over time, therefore testing long-term assumptions like their constancy. John Wheeler, a physicist, even suggests that every observation has the potential to influence the past and future of the cosmos, which would fundamentally alter scientific methods. Considering how theoretical suppositions affect data collecting, it is essential to look at these fundamental assumptions. History has demonstrated that major shifts in social attitudes have resulted from disruptions in scientific ideas, such as the transition from geocentrism to heliocentrism or the discoveries of evolution and relativity. An impact on our knowledge could be anticipated from any upcoming cosmological scientific revolution. According to philosopher Robert Nozick, theory becomes crucial when additional scientific research is unable to adequately address a subject. The question of whether theory is required to address cosmological principles is still up for dispute. It may become necessary to completely rethink our understanding of the cosmos if altering current models proves insufficient. Our understanding of the cosmos has changed as a result of continuous improvements in observational technologies. Astronomers may now go farther back in time than ever before thanks to the James Webb Space Telescope's state-of-the-art equipment, which capture light from the early cosmos that has traveled billions of years to reach us. This capacity has transformed our understanding of astronomical history by revealing trends and irregularities that contradict conventional wisdom. The possibility of reconsidering the chronology of astronomical development is among the most significant ramifications of Webb's discoveries. For instance, doubts concerning the nature and speed of galaxy evolution are raised by the discovery of mature galaxies just a few 100 million years after the Big Bang. This impression raises the possibility that the cycles controlling the development of stars and galaxies were more intricate and fruitful than previously thought. Huge-scale star formation may have happened far earlier than current models predict, according to the implications of this challenge to assumptions about the continuous growth of huge structures. Furthermore, Webb data, along with the discovery of extraordinary patterns in the cosmic microwave background radiation, show that our universe may be more homogeneous and isotropic than the Big Bang scenario can adequately account for. Discussions concerning the likelihood of a multiverse, in which our world is but one among many with distinct characteristics, have been sparked by this. In addition to redefining our understanding of physical rules, such a worldview would expand the scope of scientific investigation because it may be impossible for humans to directly observe other universes. The possibility of finding habitable zones surrounding far-off stars on exoplanets has rekindled interest in astrobiology as cosmologists continue to examine the Webb data. Examining these exoplanets' environments may provide information about the molecular markers of extraterrestrial life. Finding biomarkers, substances that might suggest the existence of organic processes, is of particular interest to researchers. Important philosophical questions concerning our position in the cosmos, and if we are alone in the vastness of space, may eventually result from this inquiry. Furthermore, two of the universe's most mysterious elements, dark matter and dark energy, have been re-examined in light of Webb's latest discoveries. The distribution of massive structures and the discrepancies in galaxy rotation curves could point to new links or particles that don't fit the current theoretical framework.